Hello and welcome to our lesson on angles of elevation or depression and bearing. So we've talked about some different classifications for angles, like what does it mean for an angle to be acute or obtuse, or those different types of classifications. We've talked about, angles measured in radians, angles measured in degrees, and then partial degrees being decimals or minutes and seconds. We've also talked about angles being drawn in standard position. So we're going to add in a couple of terms today, that way we can solve some new scenarios. So first let's talk about angles of elevation or depression. The concept, not too bad. An angle of elevation is what you might imagine. It's an angle that's created by rotating up, but it's got to be up from a horizontal line, so almost like our angles in standard position. So imagine like this is our positive x-axis. If we rotate up, we're creating an angle of elevation. Or if again this was our positive x-axis, we could rotate down, and that's going to create that terminal side, an angle of depression. So I like to think of them as angles in standard position, but they don't have to be. As long as we start at a horizontal, if we rotate up, we call that an angle of elevation, and if we rotate down, we call that an angle of depression. So an angle of depression, again, created by rotating down from some horizontal. I often like to think about it as a horizontal line of sight. So imagine yourself looking straight forward and creating a horizontal line of sight. And so that becomes your baseline. And then if you, let's say, look down at something on the ground, then the angle that's created from your original horizontal line of sight to that thing on the ground becomes an angle of depression. Or if again you have your horizontal line of sight and let's say you look at something up in the sky, then the angle created by you looking up from that horizontal line would be an angle of elevation. Okay, so let's look at a couple of examples where we might be able to use the new terminology and hopefully some old skills to solve. So number one, Pat Porterfield, nice name, I just took this out of a book, knows that when she stands 123 feet from the base of a flagpole, the angle of elevation to the top of the flagpole is 26 degrees 40 minutes. If her eyes are 5.30 feet above the ground, then find the height of the flagpole. So what I would say is we should draw this out. And making an accurate picture, or the ability to make an accurate picture from the situation, is probably one of the most crucial steps to any of the things we're going to do today. So we've got Pat, and I am not an artist, so I'm going to draw Pat as a stick figure. Her eyes, again, looking straight ahead, create this horizontal line of sight, and what she's looking at is a flagpole. So let me put a, excuse me, put a flagpole over here. And here's my flag, and obviously this is going to be the ground. Okay, so she looks straight ahead. That creates her horizontal line of sight. It says that she's standing 123 feet from the base of the flagpole, so I can either put that 123 feet along the ground here, or that also means that 123 feet distance from her eyes to the flagpole is going to be the same. So it says the angle of elevation to the top of the flagpole is 26 degrees 40 minutes. So the angle of elevation is actually created here. So not from a horizontal line, but if it's an angle of elevation to the top of the pole, that means she's looking up at the top of the flagpole. That's where our angle is. So this angle, which I just labeled as theta because it's really squishy in there, theta is 26 degrees 40 minutes. And if you have the setting in your calculator to be able to input an angle in that way, then you're good. Since I'm going to be limited to Desmos here, I'm going to convert this to a decimal. So this is 20. Oh no, my pen is going to be weird again. This is 26 degrees plus 40 minutes. Remember, that's out of the 60 that are in 1 degree to make the conversion. And so calculator says that 26 plus 40 out of 60. So we have about 26.6. It's 26.6 repeating, but let's just say 26.67. 26.67 degrees approximately. Okay, that's our angle in there. So if you want to try to squish it into your picture, go ahead. Let's see, what else do they tell us in this picture? It says, got the angle of her eyes are 5.3 feet above the ground. So her eyes to the ground, this distance right here, which I could also label here, is 5.3 feet. Alright, so the question is, what is the height of the flagpole? Now I can use this right triangle. Let's see if I can highlight this right triangle right here. This is what I'm going to actually be using to do my solving. So if I want to find the height of the flagpole, I know part of it's 5.3 feet, but, and that should, let me be precise here and label this. I need to figure out the rest of the height here, so I'm going to label this side x. And I'm going to again use that right triangle so that I can solve for x. So I have this angle, and then I have x as the side that is opposite. Remember, this is not what I want to do. This is a right triangle. Oh my gosh, eraser. Right triangle. I have the leg that is opposite and I have the leg that is adjacent, so I can solve this using tangent. So I'm going to say that the tangent of my 26.67 degree angle is equal to my ratio of my opposite over my adjacent. What in the world? I am so sorry. I do not know why my Apple Pen is like not happy the past couple of days. Okay, put opposite over my adjacent was 123. So if I want to solve for x and it's being divided by 123, I just need to multiply that over. So x is going to be an exact product of 123 multiplied by the tangent of 26.67 degrees. And so we go to the calculator to approximate this. And if you're in your, again, depending on what calculator you have, you could have left it in degrees and minutes if you have that setting. We're here, whatever calculator you're in, if you're in degrees, make sure that your calculator is in degree mode. So I'm going to multiply 123 by the tangent of 26.67, and then I get approximately 61.78-ish. That's probably going to be good enough. Now remember that distance that we found there, x, that's just the top half of, or the top portion of the flagpole from our picture. We still have to add on the 5.3 feet from the ground to Pat's eyes, and so that's going to get us our total measurement. So we'll say, let me go back to my calculator here and add on the 5.3, that we're looking at about 67.1-ish feet. And even if you rounded to 67, I would be totally okay with that answer. Okay, so about a 67-foot flagpole. That's a decent-sized flagpole. Okay, so let's look at number 2. And the picture wasn't horrible, I'm hoping you're agreeing. Number 2, we have from the top of a 210-foot cliff, David observes a lighthouse that is 430 feet offshore. Find the angle of depression from the top of the cliff to the base of the lighthouse. So let's start by trying to figure out a picture here. So I have this cliff, and David, oh, why, pen, are you doing this to me? David standing at the top of this cliff, okay? So he is observing a lighthouse that's 430 feet offshore. That's going to be 430 feet from him. So there's going to be a lighthouse over here. I don't really know how to draw a lighthouse, so I'm just going to make it look like a... It's terrible. Okay, just let it be. There's my lighthouse, and again, that's 430 feet offshore, so I know the distance down here is 430 feet, which means the distance here also going to be 430 feet. Now I'm going to go ahead and label it up here, because that is going to give me my horizontal line of sight. Good grief. Okay, so there's 430 feet there. It says find the angle of depression from the top of the cliff to the base of the lighthouse. So if he looks straight ahead, he's seeing the lighthouse. And then it says he's going to look down to create that angle of depression. So to the base of the lighthouse, when he looks down to the bottom, let me try that again. When he looks down to the bottom here, somewhere like this, he's creating that angle of depression that we're trying to find. So I don't know what it is, so I have to call it a variable this time. And this is a 210-foot cliff. So we're going to say that this distance here is going to be 210 feet. And I could have labeled it over here, but again, helpful to put it in the triangle that I'm dealing with. And we're going to make a 90-degree out of this. So maybe my lighthouse looks kind of bad. Let me just... I actually don't know how tall this lighthouse is, but I know in here we're dealing with 210 feet. Okay, so feel free to edit your drawings along the way if they look bad like mine did. So there we are. We're trying to find the angle. Again, we have enough information to do this. According to that angle, we have the side that is opposite as well as the side that is adjacent. So once again, we should be able to use tangent to solve. So we can say the tangent of our angle is a ratio of the opposite side, 210, over the adjacent side, which is 430. But the solving's a little different on this one. So in the last one, we were solving for x by undoing division with multiplication. Here, we're trying to solve for theta by getting rid of tangent, so we're going to use inverse tangent. So remember, we're going to take the inverse tangent of this side, take the inverse tangent of this side. So that's going to isolate our theta over here, and into the calculator is going to be the inverse tangent of our fraction, 230, or 210 over 430. And so theta is going to be approximately, calculator says, inverse tangent, 210 over 430, about 26.03. So let's go ahead and say about 26.03 degrees. And we're good. We did it. Okay, so the hard part is drawing the picture, but generally what you're trying to do is, again, figure out where your horizontal is, and then you're going to rotate up to create an angle of elevation or rotate down to create an angle of depression, but each of these situations will make a right triangle, and then we have all kinds of ways to solve for missing parts in right triangles. So we saw tangent in both of these. Maybe I should have picked a better variety, but cosine and sine are going to be available to you too, and I mean, if you had two sides, like in this picture, if I wanted to find this third side, I could also use Pythagorean theorem. So we have lots of ways to relate the sides and angles in the right triangle. Okay, so that's the concept. Now I want to introduce another term, which we call bearing. So bearing is a navigational term, but it's basically referring to the direction of motion. So when you're moving, what direction are you going? And we know the directions north, south, east, and west. Those are the ones that are going to apply here. So bearing refers to the direction of motion. And when we're just given a single angle, what we understand about bearing, or the understood fact, the underlying premise here, is that it's measured in a clockwise direction from due north. So we always start from north as our reference, and and then we wrote, oh my gosh, I'm so sorry. I don't know what happened there. Start from due north, and we rotate clockwise whatever degree measurement is given to us. So for example, and maybe I should mention, I'm hoping we know that, think about an x and y axis, you can kind of visualize this the same way, that like north, east, south, and west, this is the directional field we're looking at. So we would call this vertical here, we would call that a north-south line, and then this horizontal we would call it an east-west line. But you got to remember the direction there, that north is on the top, south is on the bottom, that west is on the left, and east is on the right. Maybe you've heard this, never eat soggy waffles. That's how that's taught in grade school. I remember it still from grade school to help me remember. But whatever works for you, hopefully you know which is which there. So we're always going to start north, and you can see it in this picture. So here's our north line, and if I wanted a 60-degree bearing from that north line, I rotate 60 degrees in a clockwise position, and then I land here. Okay, again, we start with the north line. If I wanted a 240-degree angle, 240-degree bearing, again, I'm going to rotate clockwise 240 degrees, and that's where I land. Okay, start north. If I want a 330-degree bearing, then I'm going to rotate 330 degrees clockwise from that north line, and there's my angle. So a lot like our angles in standard position, it's just instead of starting from the positive part of the x-axis, it's like we're starting from the positive part of the y-axis, but we're calling that our north. That's due north. Okay? And if we were just going south, we'd call that due south. And if we were just going west, we would call that due west. And if we were just going east, we would call that due east. Alright, lots of highlighting. Looks kind of bad, but no, actually, OCD in me is going to get rid of it so my picture looks a little better when I upload it later. Alright, so now let's look at some applications of this, and that's not where I wanted to go. Okay, so for example, find the angles inside of the triangle if the bearing of angle A to angle B is 325 degrees. So let's try to figure this out. So angle A to angle B. So angle A has a bearing of 325 degrees, which means I'm going to put my north-south on angle A, and if you want to visualize your east-west here as well. Angle A has a 325 degree bearing from or to angle B. So that means I'm going to start my rotation from north, and I'm going to go 325 degrees. Stinking pen. I'm going to go 325 degrees until I get to B. So angle B is on this terminal side here. And based on that information, we should be able to figure out the measurements of the angles inside of the triangle. So if this angle out here is 325 degrees, we should be able to find the measure of just this little angle in here, because I know that there's 90 degrees here, 90 degrees here, and another 90 degrees here, and that 90, 90, 90 makes 270. So if I subtract that out, 325 minus the 270, that's going to be what, 55 degrees? So that means this angle in here has to be 50. Why? Why? I'm so sorry. I do not know what is happening. It hates me right now. Okay, so 55 degrees here. And then finding the last angle in there is pretty simple because the three angles in any triangle have to make 180. So we have 90 already in the corner, and we have another 90 left to split between the 55 and what's left. So if I take 55 from that 90, let's see, another color here. The last little 90 minus the 55 means the last remaining angle is going to be 35 degrees. So we'll put 35 degrees in there. And we're good. Got all the angles. Okay, not too terrible except for my pen malfunctioning. Alright, next. Another application. Again, drawing the picture, that's going to be the key to some of these, so like this one. It says radar stations A and B are on an east-west line 3.7 kilometers apart. Station A detects a plane at C, so a third location, on a bearing of 61 degrees. Station B simultaneously detects the same plane on a bearing of 331 degrees. Find the distance from A to C. Okay, so that's a lot to try to take in. Again, we want to try to draw this out and make sense of what's happening. That's going to be the easiest way to go about it. So, and actually it's not easy unless you've done it a few times. So let's start with A and B are on an east-west line. Okay, so I'm going to make an east-west line. West over here, east over here, and A and B both on that line. Okay, so let me label this one A, and let me label this one B, and it says that those 2 points are 3.7 kilometers apart. So 3.7 kilometers. Then it says that Station A detects a plane at C. So we have a third point C, and that's on a bearing of 61 degrees. We want to put C out here somewhere. So I'm going to put C out here because I want to make an angle from A that has a 61 degree bearing. So maybe I'll draw that first and then you'll see why C has to be out there. So if I draw, I'm going to go ahead and make my north line right through point A 61 degree bearing. Remember, this is north, means I'm going to rotate 60 degrees this way. So that my angle is going to look something like this. And again, from there it's detecting C. So let's put C out here. So this is 61 degrees. And then simultaneously, B is detecting that same plane. So B is also detecting that plane. So it can see the same thing. It says that the bearing for that is 331 degrees. So let's draw this one here. It should make sense too. If we went from our north from B, then that's a 331 degree bearing right there. And that makes sense. 331 degrees definitely got to be the 90, 180, 270, and then a little farther to get into that triangle. So We want to try to use the triangle to do some solving. We're trying to find the distance from A to C in that triangle. Well, let's find out a little bit more information about the triangle. So we know that this angle is 61. Also know that this is a right angle total here. So if I have 90 degrees and I take the 61 away, that means inside that triangle has to be a 29-degree angle. So there's going to be 29 degrees in here. Okay? Now the pink one over here at B, that's 331 degrees, right? Yeah, 331 degrees altogether. Again, let me take out the 90, the 180, and the 270 there to figure out what's left. So if I take away the 270, that means I have 61 degrees left here. So this is a 61-degree angle. Now let's find that third angle. So I have lots of colors going. 61 degrees and 29 degrees. Well, that's the 90. Oh my gosh, I just did that math a few minutes ago. So if those two angles make 90, that means that this last one has to be 90 as well. So my picture is a little off, but I have a right triangle. Great news, I have a right triangle because I can use lots of different things to do solving in my right triangles. So the ultimate question is the problem here is finding the distance from A to C. So that is going to be what I'm going to call X. And I need another color, so let me just call it X. And maybe my picture's looking a little clogged. Let me redraw over here. Same thing, just so maybe you can see it a little bit more clearly. I'm trying to find this side, and I know that this angle is 29 degrees. I just want to chuck this thing. 29 degrees in here. This is 3.7 kilometers here. And I also have the other angle, but I don't even think I need it because I have already enough information to solve. So next to that 23 or 29 degree angle, adjacent to that is the side X, and the hypotenuse of this triangle is 3.7. If I have the adjacent side and the hypotenuse, I can use cosine to solve. Now if you want to use the other angle, that's totally fine. You're just going to end up using sine instead of cosine. But since I'm good here, I'll say the cosine of my 29 degree cosine of my 29 degree angle is going to be equal to my adjacent side over my hypotenuse. So solving for X means simply multiplying over the 3.7. So X is going to be 3.7 times the cosine of 29 degrees, which my calculator will approximate for me. So let's go 3.7 multiplied by the cosine of 29, and I just want to make sure I'm still in degrees. Yep. Okay. So this is 3.24-ish, or units kilometers. And we're good. Okay. So first application, using bearing when just a single angle is given. Then again, it's understood that we're going to go from north and we're going to rotate clockwise whatever the degree measure is. But sometimes we look at bearing in another way. A second method for expressing bearing starts again with a north or south line, so it's north or south this time. So it's a north. Oh my goodness, my pen. The struggle is real. North-south line, and then we're going to use an acute angle to show the direction of rotation from that either north or south line. So you're going to have a north or south, and then you're going to have an acute angle that will go east or west from that line. So for instance, I have some pictures down here that probably explain better than what I'm trying to say. If I wanted to express a bearing of north 42 degrees east, that means start on the north and then rotate 42 degrees east. If it's south 31 east, you're going to start on the south and go 31 degrees east. Okay, south again, but 40 degrees west, rotate 40 degrees in the west direction. If it's north 52 west, so again, start on the north and go 52 degrees west. So you're either going to start on your north or your south, depending on what it says, and then you're going to rotate toward, if it says east, you're going to go east, which would be to the right. If it says west, then you're going to go west, which would be to the left. Okay, and those will always be acute angles in there, so these will always be acute angles in our pictures. Okay, so let's look at a couple of applications of this, trying to apply the concept here. For example, number 5a. It says, find the bearing of a plane located at the following point on the coordinate plane, so like on a graph. If I was to graph this point at 0, -5, 1, 2, 3, 4, 5, right here, what's the bearing? Well, again, the graph could be considered just like our north, east, south, and west. So that is due south, like we're straight going south there, not just like if we were going straight up it would be north. So we could say due south as an answer. Now if we wanted to give this with something similar to like what we saw just a second ago, technically you could say that it's this is so frustrating. South, goodness. So here it is, right? Here's our angle. We could just say that it is south and oh, why? Stop. God. I don't want to redo this whole video because of this dumb pen. We could say south, and then we could say 0 degrees east, or we could say south and 0 degrees west. It just seems like overkill to say that if we're going due south. So this would be the preferred, although technically the others would be the same. So if you saw bearing in this method with the 0 degree east or 0 degree west, then that's strictly south. Or the same if it had north. Okay, let's try one that actually includes a little bit of work. So this one, we're looking at a point at 3, 4. So 1, 2, 3, 1, 2, 3, 4. There's our point. And we're trying to figure out the bearing here. So the bearing, which means we had to start north because we're in this quadrant here. Why? Why does this thing hate me? Nope. I just have to undo until it goes away because I try to erase and that just... Goodness. So obviously here is our start on north. I'm so frustrated. I don't even know what to say. I'm just going to not say anything when this happens and you'll just have to deal with me deleting. Okay. Maybe I'll just change colors. Maybe it's green. Doesn't like green. Okay, we're in quadrant 1. So there's our north. And then we're trying to get to this point here at 3, 4. So we can see the angle that... We can see the angle that's trying to be created is a north angle because we're starting on a north line. And then if I got to get over to this point, that I'm going east to get to that point. So I know I'm going to be a north and then east bearing. I just got to figure out what are the degrees east that I'm going. So let's make a triangle out of this because again we know how to do things in solving with these triangles, and if I draw that horizontal there, it's a right triangle. And I know that this distance here was 3 along the x, this distance here was 4 along the y. And so now we can find the angle measure in there that we need. And we could do this a number of ways. If we know our Pythagorean triples, we also know that that hypotenuse is going to be 5. So if we have all 3 sides, we could use sine or cosine or tangent, whatever makes you happy. If you weren't seeing the 5 and you were just going to use the 3 and the 4, or if you didn't want to use Pythagorean theorem and calculate the 5 and just use 3 and 4, then we're going to use tangent. So the tangent of our angle, because it's a ratio of the opposite and adjacent legs, which is what we have. So opposite of that angle would be 3, adjacent to that angle would be 4. And since we are trying to undo tangent to find theta, we're going to take the inverse tangent of both sides. And so into the calculator, we'll say theta is equal to the inverse tangent of 3/4. So theta is going to be approximately, let's see, about 36.87-ish. And I would be totally okay if you just rounded that to the nearest degree, because I didn't give myself a lot of space. So I'm going to say about 37 degrees. So north
and then 37 degrees east. This is really testing my patience. Just let me write a 7. Okay. Here, one more problem, and then this thing is getting chucked. Alright, let's go. Last one. Save the best for last. Now, it's pretty similar to the others. So, a ship leaves port and sails on a bearing of north 47 degrees east for 3.5 hours. It then turns and sails on a bearing of south 43 degrees east for 4 hours. If the ship's rate of speed is 22 knots, which is just nautical miles per hour, find the distance that the ship is from port. Okay, so let's try to draw this out. Okay, let's start with maybe not so big. Let's start with here's the port. Okay, on my northeast southwest line. Okay, there's my port at the origin of this thing, and it says it's going to sail away from that port on a north 47 east bearing. Okay, so then my angle is going to be created here, starting at the north and then rotating 47 degrees, and it's going to go out there for 3.5 hours. I don't know how long that is, but let me just draw this here. So again, this is a 47 degrees, and I rotated toward the east. And because this is, I'll leave that for a second. We need to figure out that length, and we can actually do that because it's traveling that bearing 47 north 47 east for 3.5 hours, and we know the speed is 22 knots, so that's 22 miles per hour. So if I multiply, we know this formula, distance is rate times time. So the distance traveled there, in that case, would be that rate of 22 nautical miles per hour times 3.5 hours. So 22 times 3.5, I'm asking for my calculator, thank you. 22 times 3.5, we get 77. So now this is going to be 77 miles. Need units. Okay. So from there, right, it goes north 47 degrees east for 3.5 hours at 22 knots. That goes 77 miles with that bearing. And then it turns. So it's going to turn from this point, which means I need another north, south, east, west line. And it says it's going to, when it turns, on a bearing of south 43 degrees east. So I would start on the south here. So I can try to show you. I would start on the south here, and I'm going to go 43 degrees east. So if I start on the south, let me try to draw this, and I go 43 degrees. Pen. Now my pen is frozen. I cannot catch a break. Nothing. Nothing, nothing. Oh, okay, I'm back. So south, but I want to go 43 degrees east. So my bearing is going to look like this. My line is going to look like this. Okay, again, on the south with a 43 degree... 40... south, and then if I go toward the east here, 43 degrees. That's what that's looking like, okay? And that's going to go, I don't know, to some distance. What's that distance going to be? Again, that was 4 hours at 22 knots. So 22 times 4 means 88. Technology. It's great when it works. This was 77 over here. Okay, so this is going to be 88 miles here. Okay, so we're going north 47 east for 77 miles, and then we turn. We're going south 43 degrees east for 88 miles, and that's where we land. So then it asked us to figure out the distance the ship is from the port. The ship from the port So this is our distance that we're looking for here, and we can call that one x. Okay, so how do we figure out what x is? Well, we first have to know what kind of triangle we're dealing with, okay? So maybe you don't want to clog up your picture, but if this is 43 degrees in here, right here, that's where I'm looking. Well, actually, let's start with this. If I dropped this down, okay, then I could technically make a right triangle out of this, and I'll show you why I'm going to do this in a second. So this is another right angle over here. If I have 47 degrees here, that means I have 43 degrees in here. And if that 43 and that 90 are subtracted from 180, that means there has to be 47 degrees in here. So hopefully you're following. If that's 47 and that's 43, that means this is another 90-degree angle. So what we have for ourselves is a right triangle. Okay, so let me clean up my picture again. It's a big mess right now. Separate this out. I have a right triangle. I've got a 77 over here. I've got an 88 over here. And it doesn't even matter what those angles are now, because all I'm looking for is this last distance. And the third side, the hypotenuse of our right triangle, we can find using the Pythagorean theorem. So even though my picture got a little messy, it got me exactly the information that I needed. So now we're going to solve by saying 77 squared plus 88 squared equals x squared. And let's just go to the calculator. This means x is going to be the square root of all of this. So the calculator is going to... I was trying to avoid writing because of this pen issue, but it got me one more time. Okay, so let's go square root of 77 squared plus 88 squared. And so we get approximately 116.93, and these would be miles. So even though it traveled 77 miles and then another 88 miles, which is 165 miles total in travel, it's only 116.9 miles from where it started because of the bearing as it traveled. Okay? My gosh, I'm so sorry about my technology problems. If that was very distracting in the video, my apologies. Mute me. I don't know. I'm going to try to figure out why my pen is being so silly. In the meantime, I hope you have enough to work on your assignments. And if not, please reach out and I will help you as best I can. Until next time, take care.